Welcome to this module of Professor Messer's free CompTIA Network Plus certification training course, the online training course that leaves your breath minty fresh. I'm James Messer, and in this module, we're going to talk all about common networking protocols. This is a great place to start. This is from our N10-004 section 1.1, where we need to explain the function of common networking protocols. There are a lot of protocols in this module and a lot of acronyms we have to go through. And I put a few here on the screen. These are copied and pasted directly from the CompTIA Network Plus requirements: TCP, FTP, UDP, SSH, POP3, NTP, a lot of different things here. What we're going to do is consolidate these together. We're going to organize them. And by the end of this video, we're going to step through everything that's here in part one, where there are link protocols, internet protocols, and transport protocols. We'll learn exactly what all of those things mean. Let's start by organizing all of these crazy protocol names into something called the TCP/IP protocol suite. You'll often hear this referred to as the Internet Protocol Suite, because that's what the IP in TCP/IP stands for, is Internet Protocol. This is very similar to the OSI model. In Chapter 4, we have a video that steps through the OSI model, but this is a suite that has simplified a lot of the things that are in the OSI model, and it really was created to be compatible with TCP/IP, which is the most common protocol used on the Internet. It's very easy now to take a lot of the things that we're going to look at with these protocols and put them into one of these boxes. It correlates very well with what's happening in the real world, and that's why it's a very useful one when you're organizing protocols in this way. There are 4 sections of the TCP/IP protocol suite: the application layer, the transport layer, the internet layer, and the link layer. If we wanted to visually understand what happens with this Internet Protocol Suite, this is the way we can do this. This is something that I created so we could get a feel for how different devices communicate to each other. So in this column on the left side, this is a computer or a device on the network. On the other side is another device on the network. And what happens, your applications that you're using are going to want to talk to an application on the other side. So logically, those two talk to each other. They have no idea what happens under the surface. All they know is that your web browser needs to talk to a web server. Something happens up there. Underneath that piece is something called the transport layer. Again, these two devices know they have to talk to each other some way. They have to address each other at a very high level. Device A needs to talk to device B, and we do that through this transport layer of communication. Below that now, we're getting into more of the networking side of things down at lower layers, the internet layer, for instance. The internet layer has things like internet addresses, IP addresses associated with them that then go out perhaps over an Ethernet connection. I've put in here these different network links so you could see in the middle, what if you needed to be routed to another connection? Routers only work at the link in the internet layer. So your traffic, as it starts at a web browser, flows all the way through this particular set of suites of protocols on your computer, goes out to a network, might go through a router, which only looks at the data up to the internet address and says, oh, you need to go over there to device B. Let me send you out another port that's on my router out to another network, where it's going to go into that device and all the way up this stack so that the application can use it. That happens every single time a packet goes into or out of your computer. It seems very complex when you look at it this way, but because we've created application protocols and network protocols that work at every single one of these layers, it's a very common and very standard handoff to be able to take things from a web browser and have it end up on the other side at the web server and finally back to you. What I did was take all of those protocol names that we have in our Network Plus requirements, and I put them on the screen so that we could see what these different protocol suites really are and where these protocols might fit. You can see there are a lot of those protocols that go into the application layer. We're not going to look at those in this video. That's in our next video. We're going to focus today on the transport layer, the internet layer, and the link layer. And you can see the different protocols that we have listed in each one of those. Let's start down here with the link layer. Because the link layer is at the bottom of our stack there, it really is in charge of, at a very low layer, making sure that one device can talk to another device over the network. And one of the primary protocols that's used for that is something called ARP. That's the way we refer to it. We rarely call it address resolution protocol, but that's exactly what's going on there. When you first communicate out over a network, the network has a fundamental way of communicating. And in Ethernet, it uses something called MAC addresses to be able to communicate. Every device on the network has a different MAC address and is a fundamental address on how these devices communicate back and forth. These devices, those MAC layer interfaces on your Ethernet cards, they don't know anything about IP addressing. That's up higher in the stack inside of your computer. So to be able to take this idea of I want to talk to 192.168.1.2, that IP address, we first have to find out what's the MAC address that's going to be able to get us to that device. And that's what ARP does for us. ARP behind the scenes, we never see it working, but it's always there working for us. Behind the scenes, ARP is responsible for taking this idea of an IP address and asking the network, hey, does anybody out there have this IP? And if you do have this IP, could you tell me your MAC address? Because I need to send you some data, and the only way I can send you data is if I have your MAC address. If you wanted to look at the ARP table in your computer, you could go to a command prompt and type ARP-A, and it's going to tell you for the interface you happen to be on, here's all the other IP addresses that I know about, and here is their physical MAC address for those interfaces. So anytime it needs to communicate to 239.255.255.250, it actually sends packets out to this physical MAC address. Just a very simple thing behind the scenes, but it's extremely important. It's very fundamental. Without ARP, nothing can communicate across the network. Let's move up a layer in our internet protocol stack to the internet layer protocols. And we'll start with one called IPv4. This is perhaps one that you're very familiar with because this is really the most common protocol that you'll find at the internet layer going over the internet. Normally, we just call this TCP/IP. It really is IP version 4. That's a little bit different than IP version 6 that we're going to talk about in a minute. That's why we usually will abbreviate this as IPv4. IP version 4 has something called a 4-byte address that ends up being 32 bits in size, which means total I can have over 4,294,000,000 different addresses, 2 to the 32 addresses. And you may have heard, if you're working at all in the industry, that we're running out of IPv4 addresses, and we do network address translation. There are many ways to conserve addresses on the network. Something we have to think about because in the big scheme of things, 4 billion isn't really that large of a number. How are we going to keep this internet going with only that number of addresses? We'll talk about that in a moment. You'll always see these written out in what we call these dot decimal notation. These are decimal numbers and they have dots between them, 192.168.3.1. It's a very common way of us human beings looking at internet protocol addresses. The details of this address format is in section 1.3. We have a video just for really breaking out IPv4. What does this really mean? What do each one of those little decimal areas mean? What is it really broken down into? So if you want to know more on that, be sure to check out that video. We really consider IP to be what I consider to be the moving truck of the internet. IP doesn't care what you stick in the back of the truck. Its job is to get data from one side of the internet to the other side of the internet. And that's it. That's all it cares about. Whatever you stick in the back, there could be video in the back of the truck. There could be audio in the back of the truck. There could be part of a file that you're transferring in the back of the truck. IP doesn't care. It has one job, and that's to take an IP address of the destination and drive to that address. And once it gets to that address, it's actually up to something else to be able to unload the back of the truck. So just think of IP that way. It is the way that we move data back and forth, no matter what type of data it is, where it comes from, where it's going to. It's really the mainstay of moving data from one side of the internet to the other. The latest version of TCP/IP is IP version 6. We just kind of skipped over version 5 and went right to version 6. This is really considered the next generation of the protocols that will be running across the internet. We're not quite there yet with the technology, but it's certainly one that's coming, primarily because we're going to have a lot more addresses available to us. Notice we now have 128 bits in an IPv6 address, which means we can have over 340 trillion addresses. Now, ideally, we aren't going to need more than that. I think that'll really keep us for a while. It really is going to also improve a number of other things. There's more security with IPv6. We're building in better routing with IPv6. It's a much more efficient protocol in many ways. We have not gotten to the point where there are widespread implementations of IPv6, at least not at the moment, but it is rapidly growing. There are large organizations testing it and starting to use it now in their environments. So you'll see a lot more IPv6 as we go along. When you start to see IPv6 addresses, though, they aren't those 192.168 decimal dotted notation that we saw before. They are represented in hexadecimal. And what you're going to see is 8 different groups of hexadecimal numbers all stuck together. We also, in section 1.3, go into details about how that's designed, how you can abbreviate some of these things, what those groups of hexadecimal digits mean. For this particular video and understanding the protocol itself, just understand if you ever see an address that is that big and long, it's an IPv6 address. Another internet layer address you'll often see is the Internet Control Message Protocol, or what we commonly refer to as ICMP. ICMP is really used at a management layer to be able to understand more about what's happening between two devices on the network. It doesn't really use IP. It has its own type of protocol method that's used to communicate between those two. And in that way, it really helps because a management protocol needs to be separated out from the other things running on the network. This allows us to do things like use the ping command, where we send out what we call an echo request to a device saying, if you're there, please respond to me. Send an echo reply back to me. If a device is not there or we're not able to communicate to a certain network, we'll get a message saying that that destination was unreachable. Here's a really good example. I tried to ping a device that was at 192.168.121.2, and my router said, I have no idea how to get to that network. But instead of having those bits just fall on the floor and I have no idea what's going on, ICMP was responsible for sending a message back to me saying, I wasn't able to get to that network. The destination host is unreachable. I have no way to reach that particular network. Again, just another way, especially if you're troubleshooting the network, on how you can understand more about what's going on behind the scenes. And it's all ICMP that allows us to do that. Here's a more interesting and in many ways a more advanced internet protocol called IGMP, the Internet Group Management Protocol. This particular protocol is really specialized because it is used for something called multicast. And multicast is a methodology of communicating across the network that improves efficiency and bandwidth, especially with types of data that need to be viewed by many people simultaneously. And what I've done is create a little map of this to give us a feel of how IGMP is used. This is an example where on one side of the network, on the internet, I have a streaming video server. This is a very common use of IGMP and how it's used. And on the other side, I have these client machines that would love to be able to watch those videos. Now, if this was a very simple video communication, you would ask the video server, please send the video to me, and you would watch it. When that's fine if it's only one user. But what if there's more than one user? You don't want to have multiple people requesting the same video from the same server and having that server send out multiple streams of video that essentially was exactly the same. Maybe a live video of a basketball game, a sporting event, or some other type of event that is sent out live. You may want everybody to view that. And here's the secret. Here's the way that IGMP fits into this. What you have all the way through this link, the network, are routers and switches that know about these multicast protocols. And we use something between different routed networks called the Protocol Independent Multicast, or PIM protocols. These use something called a subscription. This is not like a magazine subscription. This is a technical term that refers to the way that other devices on the network can hold their hand up and say, I would love to get a copy of that video that you happen to be sending. So what you have is the streaming video server sends out one stream to a centralized router, which then has other routers out there across the network that would subscribe to that video and say, I would like to watch that video, please. And the video is then subscribed and sent down to that local router. Here's the secret. Back on this local network, you've got maybe one client, maybe two clients, maybe 100 clients that would like to watch this live streaming video. What they do is send an IGMP subscription to their LAN switch. The LAN switch passes that to the local multicast router and says, please send a stream, a copy of that multicast traffic over to every single client that happens to send a subscribe request. And that means that I only have to send one packet out of my streaming video server, and yet I'm able to have hundreds, thousands, perhaps even millions of devices out on the network able to watch that one video by really minimizing the bandwidth impact across these much slower wide area network connections. Now, the applications that you use to be able to do that and the servers that are using these protocols have to be specifically written and specifically able to use those multicast protocols. For instance, if you go to YouTube and you watch a video, that's not using multicast. That's using what we call unicast. It takes the video from YouTube and transfers it to your machine. If the person sitting next to you requests that same video, they're getting a completely different stream of data, a completely duplicated stream of data sent to their machine. Not very efficient. But in most cases, the vast majority of streaming video that's done on the internet today is via unicast. And you can start to see why in very specialized environments, this multicast helps a lot. You see it a lot with live presentations. You also see it a lot with stock quotes. When one system can send out one stock quote that many different people can get at one time. A very simple, efficient, and very easy way to send that very important data out to multiple devices simultaneously. Let's move up the stack a bit and start looking at transport layer protocols. The one I'd like to start with is one called the Transmission Control Protocol, or TCP. This is the TCP in TCP/IP. This is a pretty popular protocol, primarily because it is what we call connection-oriented. It sets up a connection between two devices and it confirms that data can be sent in both directions. We call that a reliable delivery of that particular protocol. Because this sets up a connection, it keeps track of all the data going from point A to point B. It also can manage out-of-order messages or retransmissions. And it does that by sending data to the other device, and that device sends back an acknowledgement saying, "Thanks for sending the data. I'm just letting you know I received it properly." And if those packets happen to come in out of order, or I'm missing a packet in between, it can send a message to the other side saying, "I missed a packet, can you please send that?" And then when it receives that packet, it can put everything back in the right order and then process it further with the application. We talked earlier about IP being the moving truck of the internet, and it doesn't care what's in the back. Well, it's TCP that does care what's in the back. Its job is to load the traffic into IP and unload it when it gets to the other side. And it has a manifest, and it looks at the manifest and says, did I receive all the packets I was looking for? Did all the moving trucks show up? If a moving truck was missing, it tells the other side, you need to send that moving truck back with that copy of that data so I can unload the cargo and put it all back together again. That's the job of TCP. There's another type of transport layer protocol that works a little bit differently called UDP, or User Datagram Protocol. Unlike TCP, UDP is connectionless. It doesn't care if there's a connection set up or not. It's very casual, just sends packets out. Doesn't even know if the other side's going to get them or not. And in fact, the other side doesn't even respond back if it received it or not. That's not the job of UDP. The application itself might say that it didn't receive the data and have to retransmit, but UDP is not going to do that for you. At this transport layer, we call this an unreliable protocol. There's no reordering of data. If it comes in out of order, that's too bad. We've missed it. If there's data that wasn't received, UDP does not ask for a retransmission. It's very simple about that. It doesn't care about the data being out of order. Again, it's in charge of loading and unloading, but that's it. If it doesn't receive something, it doesn't send a message back to the other side saying, please send another moving truck. It simply decides, well, I missed it. You see UDP used a lot for things where you don't have time to send traffic back through the network. For instance, if you're doing streaming audio, streaming video, voice over IP, especially where it's real-time data, or I'm watching a live event happening and I happen to miss a packet, I can't stop my conversation and rewind my conversation and fit the packet back into that. If I miss a packet, we just miss it and we keep going. If I missed a lot of packets and you didn't hear exactly what I said, you're going to have to ask me to say it again. That's just the way that our live communication works at a human level. And you see, most often it's UDP that does that for us. Let's see what we've learned about our common networking protocols. Our first question here is, what is the primary responsibility of the ARP protocol? Well, if you remember, that's our address resolution protocol. So it would make sense that that address resolution protocol be able to map protocols like IP addresses to our MAC addresses and at a fundamental level allow devices to communicate across our networks. Our second question, at what layer of the TCP/IP suite does UDP, our user datagram protocol, reside? If you recall, we had those stacks, those layers down the right side there as we went through, and UDP is at the transport layer. And lastly, what is the primary responsibility of IGMP? And the IGMP protocol, the Internet Group Management Protocol, is in charge of managing the membership and those subscriptions of those multicast groups as we send that live streaming data out over our networks. That brings us to the end of our Common Networking Protocols module from Section 1.1 of our N10-004 exam. And now you should have a pretty good idea of those different protocols that occur at the link layer, the internet layer, and the transport layer. If you'd like to see any of our other Network Plus videos, you can participate in our message boards, send me a message, or much more. You can visit our website at freenetworkplus.com.